everyone. Now it's time to start the competition. Firstly, introduce ourselves. So start from the jury and the team member later. So I'm Lan Yanwen, from National Taiwan Normal University. Okay.
张吴哲48559。蒋希胜from National Taiwan University。
My name is Chen Hongyi, from 48557。
Hello everyone, I'm Yang Jiahui from Bongjia University. Thank you very much.
Okay, next, let's introduce the team member. So if later if you want to introduce your team name, especially you also can certainly introduce. Let's start from the reporter.
Good afternoon, everyone. We're team mining, and for this name, I hope that all my teammates can be energetic, no matter facing what frustration. And this is Jeremy, this is Jan, this is Carol, and this is Wayne.
Okay. So next from the reviewer.
I'm the team leader of the team Toddy. I'm Liao Yisheng. And this is Xu Chenyou, Chen Bingxiang, Lan Pujun, Wang Zhijie.
Okay. Next.
Hello, honorable jurors and fellow competitors. We are a team Excel here, and I'm the captain Li Yushen. I'm here with my teammates He Yingrui, Chen Yihong, Zhong Jian, Wen Jing.
Okay, thank you. And this section actually they all fixed the topic already. So now, let's move on the first one. So the preparation for the reporter, 5 minutes. Okay, so please write down your name on the blackboard. so now you can start.
Okay, honorable juries and fellow competitors, I'm the reporter today. My name is Shen Yichen, and today is problem 10, droplet explosion. So, let's move on the problem statement. When a drop of a water mixture is deposited on the surface of a hydrophobic liquid, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. So here's my contents. First, we'll start at the observation and the theory, and then it's the experiment, and that is the conclusion. First is the observation, and we can see the blue mixture is originally high in the concentration of this center, and when the times go by, the liquid starts to spread on the surface of this hydrophobic liquid, and then so it will cause the spreading, and while the droplets fragment into smaller droplets. So we conduct some observation for different concentration, and later found that the reaction of the 50% first reaction in the 40 seconds is the same as the final droplets. So we can determine that a part of the reason that this phenomenon happened is about the evaporation of the alcohol and then decrease the concentration of the mixture. So it's there, and here's the third discussion. So as we can see in this chart, the alcohol is dripped on the oil, and the surface tension of the oil is greater than the alcohol. And as we see here, the gamma is present at the surface tension. So the surface tension of the oil will pull the alcohol inverse, and then you can see on the size of the alcohol is thin, so it starts to evaporate. So it will cause to fragment. And when the times goes by, and we will see that this will fragment into smaller droplets, fragmentation, and the evaporation of the alcohol will still working. And so let's talk about the surface tension. Due to the cohesive forces and the molecules located away from the surface is pulled equally by every direction. So that is results for a net force of 0. But the molecules on the surface doesn't have the same molecules on the sides. So therefore, they are pulled inward. This creates some internal pressure and forces the liquid surface to contract into the minima area. So this interesting phenomenon has a previous investigation known as the Marconi effect. The Marconi effect is simply means that the surface gradient of the different fluids, and we can see here there's so low surface tension and the high surface tension is generated. So let's move on the experiment setup. First of all, I used the cardboard box for facilitate shooting, and I put the ball inside the box, and I also opened a hole on the sides for facilitate dripping. And we used pipetter to control the volume of the droplets, and the volume is 150 ml. So for the analysis details, the analysis program I use is MHJ and Excel. So first, I sketch a picture that I get from my video, and then I'll analyze using the MHJ, and to get the summary as it counts and the area and the results for the area each droplet. So and how do I calculate for the surface tension of the oil? And I use the drop weight method to measure. And this equation is get from this reference. So we have to first of all calculate the mass of the of the droplets, and then it's the dropper radius. But there is a correction value to consider. So as the radius of the dropper and over the volume of the droplets. So here's the calculation I get from this equation. And here's the video that shows that how I did the drop weight method. So, and for the surface tension and the alcohol, and I get from the theoretical value is the red line, is the yellow line, and the blue dots is the measurement value that I get, and the red dots is the average of my measurements. So, and for the temperature and the surface tension of the alcohol, I use this website to know the surface tension with the relationship with the surface tension and the temperature. So for the experiment, first of all, I choose 4 types of variables and consider that different parameters. And the first is different types of oil, and second is different thickness of oil, and the third is different concentration of alcohol, and the fourth is the different temperature of alcohol or oil. So as a different type of oil, I choose sunflower oil and soybean oil and grapeseed oil, and then we can see that as the calculation mentioned, the surface tension of sunflower is greater than soybean, and the soybean is greater than grapeseed. And here's my experiment video. And here's the right-hand side above. This graph is about the droplets count when the time goes by, and the bottom side is the area for the droplets total area, and when the time goes by. The next is the grapeseed oil, and the last is soybean oil. So for different types of oil, I think there is a positive correlation between the surface tension and the results. And as we can see, the sunflower oil is 34 is greater than the soybean and the grapeseed, and we can see the fragmentation and the droplet counts is bigger than the soybean and the grapeseed. Okay. So for different thickness of oil, and I use the ruler to measure the thickness of the oil. And I use 1 centimeter, and then the 2 centimeters, and lastly is the 3 centimeters. So I compare these graphs, and that I get from these graphs is larger thickness has a faster fragmentation. Also, I want to say that I use the same type of oil to consider the different thickness. I use sunflower oil. So for the different concentration of alcohol, first of all, I use 50 Celsius, but there's no increase or decrease for the count, but there is an increase for the area change. And then next is the 70%. And lastly is the 95%. But because of the 95% is too hard to analyze, so I didn't did the analyze for the MSJ. And these are the graphs comparing, and we can see the different concentration of alcohol will dramatically affect the result of the final droplet. And we can see here the surface tension is just like the type of oil. Bigger surface tension is, and the results will be more obvious. And then it's the different temperature of alcohol or oil. So first of all, I use the temperature scanner and the heat plate to control my temperature that I want to use. First, I use the 50 Celsius oil and the 20 Celsius, and control the 20 Celsius alcohol. And then it's 40 Celsius, and then it's 30 Celsius, and last one is the 20 Celsius. So these are the comparing with the with the graph, and we can see there is a limit. And obviously, there is a limit for the fragmentation phenomenon. I think it's between the 30 Celsius and the 40 Celsius. And we can see the graphs difference. And then it's to control the total temperature of the oil and change the temperature of the alcohol. And then it's the 30 Celsius alcohol. And the last is the 40 Celsius alcohol. So the same, these are the calculations that I get from the website. And so we can see same as the types of the oil, the greater the surface tension is, the fragmentation will be more obvious. So why is there such a rapid rise in the front of the chart? Because of the fragmentation that because the drop, first drop in the oil surface, it start to decrease. The surface tension is very large, and the right hand side is when the time goes by, and the changing will be go lower. So for the conclusion, first of all, it's for different types of oil, positive correlation between the surface tension and the result. And second, larger thickness has a faster fragmentation. And the third is different concentration of alcohol will dramatically affect the result of the final droplets. For the fourth one is compare the results of different temperature of alcohol and oil. The higher temperature with the bigger surface tension, the more difficult the phenomenon will happen. And the fifth is all the parameters I consider with all affect the counts or the area result. And that's my presentation. Thank you.
Okay, next 2 minutes for questions of the opponent.
First, do you think that the surface tension will affect the exploding phenomenon?
Of course, just like I mentioned in my theory.
Also, next question. Do you agree that the molar drop, the droplet that will extend infinite, that it will not go to, it is a finite, it will not go to infinity?
Yes, of course it won't go for infinity because the phenomenon has it has a surface tension gradient.
I have a question. Did you measure surface velocity in different positions? Surface velocity.
Different velocity of the oil?
I mean, do you measure surface velocity on the oil?
Oh, I didn't measure.
Okay. Do you measure the evaporation rate of the mixture?
No, I didn't measure it because of the evaporation of the mixture is really hard to measure. But I think this is a great suggestion for the. I will measure it in the future.
Do you find the boundary condition of the fragmentation?
I'm sorry.
Boundary condition, that means which that will affect the fragmentation.
Fragmentation. These 4 variables that.
All have a boundary condition.
Yes.
Oh, okay. And do you think that you said you have found the boundary condition, and do you think that the boundary condition of the concentration is same as the concentration at the rim of the drop? At that position.
Can you say it clearly?
Okay, next question. I will discuss about later. And do you think the molar drop will shrink at the end?
Yes, of course. It was stop.
And do you think that they will have a recharge force when the drop shrink? Do you have a force that
Time's up. 3 minutes for preparation time for opponent. Start. Opponent, please take the floor.
Honorable juries and fellow competitors, I'm the opponent from Team Selfie. I'm going to oppose problem number 10, droplet explosion. The problem statement is when a drop of a water mixture, like water alcohol, is deposited on the surface of a hydrophobic liquid, like vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of final droplets. And I think the main focus should be what caused the initial drop to explode, and how do different parameters affect the evolution of the drop, and what will affect the size of final droplet, like the problem statement. And because this problem is complex that we make a structural solving problem, we believe that first we should have a phenomenological definition and explanation about the droplet explosion, and by using the surface tension and that causes the Marangoni effect. And also, after that, we should analyze the exploding phenomenon of a drop, like the surface velocity, which the reporter didn't measure it, and the maximum radius of the drop, and the time scale of experiment. And after that, we should investigate the relevant parameters that affect the fragmentation and the size of final droplets, like the initial concentration, and the thickness of oil, and the temperature of the oil. And this is a strong and weak point for the reporter, that he will identify the phenomenon of exploding and not exploding, and he did well on reproducibility experiment setup, but he have a poor quantitative and correlated explanation, and he lack of a sample like the error bar, and he didn't measure a surface tension of air and alcohol mixture, and he didn't analyze the final drop of exploding or not exploding, and he didn't explain the experiment error, and he didn't have a zero down. And this is a point to be discussed. I will focus on discuss what is the definition of the final droplet, because that problem statement has said that investigate how the relevant parameters affect the final droplet. And then I will ask the reporter about what is the evolution of the drop, like how did the surface tension that caused the Marangoni effect, and how do initial concentration affect it. And then I will ask about how will the surface velocity will remain different at a different position, and I will ask about the reporter that the boundary condition for the fragmentation, and I will ask about how these parameters, like initial concentration and the thickness of oil, that cause the different result. And for the final droplet, I will also ask about these two parameters and why that it cause to this result. And also I will ask about the reporter for analyze for evaporate rate and the surface tension and the temperature. Okay, I want to skip to the next section. Okay, first I want to talk about evolution. Like you have seen that the surface tension will affect the explosion phenomenon, right?
Yes.
Then why the droplet will explode?
Because the surface tension of the alcohol, as I mentioned, the oil surface tension is greater than the alcohol surface tension. So surface tension of the oil or
You have the reporter that show that
yes.
at different positions it will have a different surface tension, right?
Yes.
Can you show that picture? Yes. And what does it cause the surface tension gradient?
It's about the alcohol surface tension and the oil surface tension. It's
May I use
already general.
Yeah, sure.
Okay. I mean, you have said that in this will have a different surface tension, right?
Yes.
But what causes it to have a different surface tension at different positions?
I don't understand because I want to say is the alcohol surface tension is already generated and the oil surface tension is already generated. So when the alcohol drips on the oil, it already
I mean,
it's a
it is a mixture, but why cause this surface? They will have a different surface tension and cause a Marconi effect.
the Marconi effect is just
I mean,
about the surface
what
tension.
cause they have a different surface tension?
It's already generated, so there is no cause.
I think that is because that if we have the initial concentration to drop at this, and they will have a different concentration. Like if they have to evaporate like this, because they have a different thickness.
I think the evaporation is on the side of, because it's thin, so it will evaporation quickly, and it's not on the center of the droplet.
Yes, so you mean that they will have a lower concentration, and here it will have a high concentration.
Yes.
And also because that if we have a lower concentration, that means the surface tension will be higher, right? So this will have a lower surface tension.
So
And
the
this
surface
will,
tension is higher, so it will hold the droplet like this.
yes, and I agree with you that because it has a different concentration of the different position of the droplet, so it will have a Marconi effect. Okay, and I will ask you about what causes stop at the rim. You have mentioned that the droplet will not go infinity. So what causes it to stop?
The main reason for causing to stop is the gradient is decreased. The gradient.
Which gradient?
The oil and the droplets mixture. The mixture droplets. The surface tension gradient is decreased, so that will make the spreading stop. So it will not always go for infinity.
So you mean that because
When
they
the time
have
goes by, yes.
they will have a surface tension between the mixture and oil. They will have a mixture and oil, and they will have a surface tension between the mixture and air.
Yes.
And this is the surface tension between oil and air. Sorry. And this is a mixture oil. That because it will have a lower, the concentration will decrease. So that you mean that
Yes.
because so the mixture oil, the surface tension will be higher and it will stop in that case. Yes. Okay. I agree with the reporter that it will have after that you will have a balance to these three surface tensions.
So it will not always go spread infinity, so it has a limit for the spreading.
Okay, after that, I want to ask about why do you say that the drop will also shrink?
Because of concentration evaporation, so it's just like a
Like the can you turn to an observation video? I mean, what caused the drop will also shrink at the point? Because you have explained that you will stop at the.
because the concentration is lower, is very low, so there's the difference between the surface tension oil and the mixture is very
You
low.
mean that this concentration will lower at the ring of the concentration?
Yes.
But you have mentioned. Oh, okay.
I mean, what I mean is the mixture 50% here and in the picture that's here. I mean the surface tension with this gradient is very low, so it will have a representation as a phenomenon.
Yeah, but why it will shrink at point?
Shrink at a point because the evaporation of the alcohol.
We think that it is because when it got, let me finish my statement. Because it got a balance and it will have a critical concentration at this point, then it will fragment. So it will, after that, it will contain a point, right?
Can you say that again?
I mean that because it got the boundary boundary concentration at this point, and after that the ring of the drop will be fragment. So this will also be smaller because they will have fragment, right? Okay, I want to ask about what is the definition of the final droplet.
For definition, I think it's the graph that I get here for my experiment.
Yes.
I think it's the right. I think it's the right side here, for the because the surface tension gradient is.
Can you play
Difference?
this video? Yes. What is the definition of the final droplet?
It's the video.
Which droplet is the final droplet?
Here, this is not here,
But
it's not present in the video.
why
Because I only show.
is the y-axis for this graph?
This is the total count for the droplets.
The amount?
Yes.
And what is this?
Millimeter square.
Which-
This is the area. This is the area.
But which area?
Total
Like
area.
Total area.
Yes.
Okay. So why do you think that if you change the initial concentration, that will affect the total area?
Initial concentration will affect the.
Do you do a parameters that change the initial concentration?
Yes. This is
Yes. And okay. Do you compare with different initial concentration that it will have a different radius of maximum? Yeah. How do you
Oh,
see
you mean the radius of the droplets? Different
the area of droplet?
area of droplets. Droplets.
How
Here.
do you show?
You mean here?
But you didn't compare.
Oh,
yes.
I compared. It's the 75% here, the orange line, and the blue, and the 50%.
Yes. So this graph shows that if we increase the initial concentration, then the area will be higher, right?
Yes.
And can you explain that?
Oh, as I mentioned, because of surface tension, as we see here, the
Do you
surface
think that
tension.
if they have a higher initial concentration, that
Let me
okay,
explain.
okay.
So because the surface tension is great, the differences between the oil and the surface tension is greater than the blue 50%. So
Why you will
the
have a greater?
fragmentation will be because the gradient is bigger than the blue one.
You mean because the initial concentration is higher than the surface tension, the delta surface tension will be higher, so it will have a larger force to
Yes,
pull.
larger surface.
So it will get a higher surface area.
Yes.
Yes. Okay. And I want to discuss about the thickness of oil.
Okay.
And how do you think the thickness of oil will affect the area?
I think it's about. About the surface tension.
In this chart, do you have some connection between different thickness of oil?
You mean here? This is the.
What is the result of this? So, I mean different thickness of oil. How will it affect? Can you explain that? If you change the thickness of oil.
I think the thickness is larger, and the fragmentation will be.
Can you draw an example? If there is a thickener and there is a thinner, then how will it affect the area?
Actually, this is not the flat surface.
Okay.
As I measured for, it's like this. So for the thinner one, it's not.
Yes.
bigger.
Okay. Well, how will it affect?
So this is the change is larger. So the fragmentation will be more obvious in
More obvious.
increase.
But
For the
Time's
and I
up.
showed in the count.
Okay. Opponent, yeah, please summarize your discussion in a minute.
okay, we have many talk about the definition of the final droplet. That reporter said is he has to main focus about the area, and also I asked the reporter about the phenomenological explanation. about how when the drop step on the oil and how it will expand to the maximum radius and how it will shrink at a point. We have discussed about that. Because it is a surface tension, it will have a different surface tension gradient. And I asked about the reporter that he didn't measure the surface velocity, and he said that he had find a boundary condition, but he didn't show in his report. And also I asked about the reporter that if we change these two parameters, that how will it affect the final droplet? And we have a conclusion about the initial concentration, but we haven't discussed that thickness of oil.
Okay. So, questions for reviewer, you have 3 minutes.
Okay, so to the reporter, can the separation and shrinkage rates of the separated droplets be observed or quantified?
Can be observed, but I didn't do the quantify.
Okay, so how do you think about, will the smallest droplets eventually disappear or will they remain?
As the time goes by, I think there's difference. I think they will disappear.
Okay, so how about opponent?
I think because the alcohol will evaporate, so after the time go by, then the mixture will be very small and then evaporate.
So you mean really small is to remain or will disappear because
Disappear because of the evaporate.
Okay.
Yes.
So if dyeing the liquid with dye, will it make the result different from the original without the dye? What do you think about it? Yes, you use the like.
Oh,
you
that
make
is
it
the
loose.
surface tension. That is the surface tension unit.
Okay. So the original central droplet will form a central circle, and all the split droplets will also form a side circle. Will the size relationship between these two circles be related to time, concentration, or?
You mean the size of the larger droplet and the smaller droplets size?
Yes, the circle.
I think it's about the time will affect.
So concentration affect.
Concentration is
And how about the different liquids?
different liquids, yes, but I didn't do the different liquids, so I think that is a great suggestion for in the future I will just do that.
Okay, so how about opponent? How
And
do you think?
we have discussed about if we increase the initial concentration, and it will have a bigger surface tension gradient, so it will have a bigger force that pull the droplet, so you will get a higher area.
So you mean that the concentration will affect the?
Yes.
How about different liquid?
I think if you change the different liquid, that it will also change the surface tension and the viscosity of the liquid, so it has to consider more.
Okay. How about to the reporter? As your report stated that it is hard to analyze the 95% alcohol. So why is it hard to?
Because the concentration is high, so the spring range is too big, so I can't. So there's no fragmentation in the first part of the video, so I can't analyze it fully analyze.
Hands up. 2 minutes for the preparation of a reviewer. Reviewer, please take the floor.
Okay, so I'm the reviewer of Team Toysy, and today I'm going to review problem statement number 10, droplet explosions. So this is a problem statement. So this is an overview of the reporter's presentation, and the theory is because the difference between the surface tension, and it will make the droplet fragment, and they have included Marangoni effect. And their setup is different types of oil and thickness of the oil and concentrations of alcohol and different temperature. And the conclusion is that there are positive correlations between surface tension and types of oil. And the larger thickness has a faster fragmentation. And concentrations of alcohol will dramatically affect the final drop, and higher temperature and surface tension will affect also. So this is the pros and cons of the reporter. The strength is that they have different parameters, and they have like reproducible experimental setup. And areas of improvement is that there are lack of main focus, and lack of investigating the size of the final droplet, and lack of connecting their theory and their results. And this is to the opponent. And they have clear-sighted question and asking question about fitting line. And areas of improvement is that they lack of the overview of the report, and they sometimes interrupt the reporter's speaking. And this is their discussion. And the first point raised by opponent is why the droplets will expose. And because the reporter response is that the oil surface tension is bigger than alcohol, so it makes it explode. And the second is that what causes the differences of the surface tension, and the alcohol is already generated. So what causes it stops and not infinity? That causes stop is the surface tension will be higher. And the point raised by opponent is that drop at a point, and the concentration of the alcohol and it will evaporate. And discussion is that what is the definition of the final drops, and it's just mentioned in the chart. And how the initial concentration will affect the area. Because when the surface tension is greater, the fragments will be higher. And how different thickness of oil will affect the result, and fragmentation will be more obvious increase. And our question, can the separation and shrinkage age can be observed, and it can be observed and quantified? And will the smallest droplets eventually disappear, or will they remain? And the report says that it will remain, but the opponent says that it will disappear because of evaporation. And if dying the liquid will affect the result or not, they said no effect. And the original, will the size of the circle related to the time and concentration? And answer from the reporter is all of them will affect. And the answers from the opponent is that the concentration will affect and change the liquid. And the viscosity of the liquid will also affect the experiment result. And so since then, we should consider more. Okay, so that is, this is all of the, this is the missing points of the reporters, and they are lack of
concluding remarks from the reporter.
Okay, first of all, I want to say that a reviewer did a question that when the droplets at the time goes that it will remain or disappear, and actually I did answer that it will disappear in the discussion, so I don't think there. So for the first concluding remark, the phenomena is caused by the surface gradient that I mentioned in my presentation, and the second is I will do more experiments to ensure the data is correct, as the opponent mentioned that the error bar is not applied. And the third is I will use different liquids as the parameters, as the reviewers mentioned. we didn't consider the liquid difference, so I think that is a great suggestion for our to do in the future experiment. And for this, I will do the calculation about the volatility of alcohol and even the viscosity of the liquid. And I did connect the theory and the experiment as a surface tension gradient. So I think that's my concluding remark. Thank you.
Okay, last one is the question from the jury.
The report narrative, you have tried different techniques.
Yes, yes.
Can you show so 1 centimeter, 2 centimeter, 3 centimeter. So 5 different thickness. These lead to different presentation.
I'm sorry?
So five the results are different.
Why are the results different? I think it's about the liquid surface difference. I mean, the higher center, the higher thickness, the larger thickness has a big difference from the surface, and the lower thickness has not obvious surface difference from the container.
Do they have the same surface tension or different surface tension?
This has a different surface tension, but I didn't calculate.
Do you think the thickness can change the surface tension?
I think yes.
I think it won't change the surface tension.
Do you have some comment on the different on the results?
I think if we decrease the thickness of oil, that it will have the same boundary layer, but the pipe flow need to get faster. Then it has to decrease the whole system that to make sure the energy is limited. So if we decrease the height of the oil, that I think the radius cannot go so further. So the area will be smaller.
I think because we are using the same oil, so the surface tension won't change.
Then the question is what caused the difference? Why result will be different?
Why result will be different? Maybe it's because when they decrease the height of the oil, they have some unpredictable effect on their surface. So
How about you? Why result is different?
You mean this result? I say that because if we change the thickness of oil, then the pipe flow will have different. So I think if we decrease the thickness of oil, then it will have the area will be smaller. But in this chart, I cannot have any result after I see this chart. It's just my own opinion.
Why smaller thickness leads to smaller area?
Can I use a dashboard?
Just show this.
Because they will have the same boundary layer like this. But if the thickness is thinner, then the pipe flow need to get faster. This is the boundary layer. This is the pipe flow. Yes, because this volume is smaller, it's thinner, but the whole energy is the same. So it has to reduce its speed. So that means the surface of the oil will reduce its speed. So the area will be smaller because the speed is decreased.
Potential questions?
Just one more question. Just more answer. Okay. Do you think the fragment droplet, the size of fragment droplet, has any parameter will affect the size of fragment droplet? The size of small droplet.
I think the thickness of oil and the concentration of the drop, and also the initial volume of the droplet that will affect.
I think the concentration and the temperature and the different types of oil will affect.
I think the different concentration and temperature and what the surface tension is will affect the result.
Okay, go in time. Okay, for the reporter. 6, 6, 7, 8, 7. Next for opponent. 7, 7, 8, 8, 8. Next for reviewer. 6, 6, 7, 7, 6. Okay, so now we take a 10-minute break.
拿走了，谢谢。不是他们的，
不是他们的。
他们说。
这是需要帮忙吗？
兄弟，你有必要聊，你先不要聊。那个简报太多了。没有，不是。你把卡掉，我第一看到傻眼，我真的看到傻眼。没有，跟我写的绝对不一样，我跟你讲，绝对不一样。这么可能一样？
热碰。
最后一场才是。没有，它是配置跟另外一个不一样，是相反。
或者侧面找到，至少一个特质。
我刚做头痛，油门看门，
好像可以开个窗吗？我要开冷气，我开冷气，我开窗嘛，因为外面
所以谢飞今天没来，没来出声，我还把我的意志传递，我的名牌现在拿了。
我在我睡觉。最后一天了啊，今天打完，明天就是看别人比赛睡觉。我等下报告我笑死。我等下报告我。
就没有，就调整好心态就好。刚才安总他说状况不是很好。
哦，真的假的？他怎么知道？他怎么知道？
不要紧张啊，你就想说来这边好好表现，就不要太在意。不好意思吗？会不会协同？我看你是协同。
一开始来的时候，
为什么？
惊讶。
可以啊，你要可以相可以啊。
你知道吗？我觉得念中文的，
我说等下开始之后就走。
其实你可以跟那个玉德交换分，也是要跟玉德交换分，就是我们在报告就是。是你问一下这个，
不好意思，是工作人员。就是观赛的话，可以问一下。
观赛吗？
对。
是知道。
对，可是我忘了带那个牌子。
好像没有工会。
可以搬一点，就是可能搬在这边，这样是不行。
指导老师是不是也会进来看？指导老师可以，好像到这个，我记得前几天有。
印象之前说1年应该都是可以。
还是那个，可能对老师没有其他的，就他那边。
我是从头的时候，
这个就是那个旁边那个椅子，门旁边那个椅子。
对，是啊，
应该是只有那边有位置。前2天看会有人坐在那里，可是我在猜应该是那个位置。可是今天已经有人了。对。
本来还是好打。
有这个吧？还有放手可能好翻一张出去。
可是里面有空的位置，还是都是工作人员？
就是
等下会走来抢去，我这边比较方便。
你说等一下，
你是去建工业，他请客，每次他吃烤肉，烤肉就还有烤肉，肯定有喝烧酒，就是你是为了不方便。14分钟啊，10分钟啊，专心考试别吃快，不一定，他们讲5面讲6分钟。
Everyone please have a seat now. Okay, now let's start the second one. So, ，Okay, in the meanwhile, please write down your name on the blackboard for the presenter. Reporter, please give your presentation.
Hello, honorable jurists and fellow competitors. I'm a reporter from Typt Excelsior. Today I'm going to report problem number 4, a single disk. And here's the problem statement. A metal disk with a hole at the center sits in a container filled with water. When a vertical water jet hits the center of the disk, it may float on the water surface. Explain this amendment and investigate the relevant parameters. And we'll main focus on the first analysis of the metal disk floating on water surface and how parameters affect the boundary condition of floating. And here's my outline for my presentation today. First, I'll talk about the preliminary experiment, including the redundant explanation. The next part is the theoretical model. I'll talk about some first analysis and calculation. And the next part is the experiment. And after the experiment, in the discussion part, I'll talk about some possible error that might influence the experiment in my experiment. And the next is the conclusion. And this is my observation video. We can see that when there is no vertical water jet hitting on the disk will sink. But now if we give a metal disk a vertical water jet hits the center on the disk, even if there's water spread out on the disk still can flow constantly. And it is because when the vertical water jet hits on the center, the water will spread out. And means that the flow velocity under the disk is smaller than the flow velocity on the top. And so from the Bernoulli principle, we can note that the pressure under the disk is bigger. So the pressure difference will cause a lifting force that supports the disk to float. And here's comes the first analysis. when the disk is floating on the water surface, and that means the downward force acting on the disk is equal to the upward force. And the downward force, including the impulsive force that caused by the water flow, and the downward force also includes the mass of the disk and also the mass of the water on the disk, like here. And it will equal to the surface tension around the disk and also the force caused by the pressure difference. And next, I want to talk about the Weber number. Weber number means the relative importance between the fluid inertia and the surface tension. When the Weber number is bigger than 1, and that means that the surface tension is relatively important. And even that the value of the water flow is a lot smaller than the range we use in our experiment, we can see that the Weber number is still a lot bigger than 1. So it means that we can ignore the surface tension at the hole on the disk. And if we want to know the mass of the water on the disk, first we need to know the thickness of the water on the disk. We can see that the thickness of the water on the disk at every point is not exactly the same. So after our experimental data, we can know that the thickness of the water on the disk is inversely proportional to the distance between the point and the hole. So we can know the K by fitting our experiment. And after after knowing the constant K, we can use it to calculate the mass of the water on the disk. And after our calculation, it will equal to this. And from the Bernoulli principle, we know that the potential energy and the kinetic energy. So then we can use it to calculate the pressure difference at the point on the disk. That equals to this. Then after we know that the pressure difference that acts on every point on the disk, then we can use it to calculate the pressure difference, the total force caused by the pressure difference, and it will equal to this. And in our experiment, I use the water pipe, and a water tank, and a metal disc, and the flow meters. And this is my experiment setup. And we use the flow meters to measure the flow rate and the flow velocity, and we use this to control the flow rate. And here's my first experiment. We want to see how will the mass of a disk influence the experiment. So here's the control variables, including the radius of the metal disc, radius of the hole on the disc, and also radius of the water flow. And we are going to measure the critical value of the water velocity that can let the disc to float on the water surface. And after our experiment, we can clearly see that if the mass of a disk increases, the flow velocity also needs to increase. This is because when the downward force increases with the gravity, and that means we want the disk to float on the surface, we also need to increase the upward force to balance it. And so we can try to increase the lifting force, and the best way to increase the lifting force is to increase the flow velocity of the water, so the pressure difference will increase too. So the upward force will equal to the downward force. And here's our second experiment. And we want to know how well the radius of the metal disc will influence the experiment. And here's the control variables, including the mass of the disc, the radius of the disc, and also radius of the hole on the disc, and the radius of the water flow, and also the distance between water pipe and the disc, and also the initial depth of the water in the tank. And we're still going to measure the critical value that can make the disc to float in different radius. And after our experiment, we can clearly see that if the area of the disc increases, the disc can float even the flow velocity is not that fast. It is because if the area of the disc increases, that means they have more area that the disc can have the pressure difference. And that means you have more, even in the same velocity, flow velocity, you have got more lifting force. So that even the area, so that if the area of the disc increases, it doesn't need that much of flow velocity
and so the disk still can float on the water surface. And in our third experiment, we're going to know how the radius of the hole in the disk will influence the experiment. And here's the control variables. The first one is the radius of the metal disk, and the mass of the disk, and the radius of the water flow, and the distance between the water pipe and the disk, and also the initial depth of the water in the tank. And we're still going to measure the critical value to see that the water velocity that can make the disk to flow in different radius of the hole on the disk. And I'll go back to that page. Okay. Next page. And after our experiment, we can clearly see that if the radius of the hole increases, the flow velocity will increase. It is because the amount of the water flow comes out from the water pipe is the same. So that means if there's more water go through the hole on the disk, that means the flow rate on the disk will decrease, so that they won't have that much of the pressure difference. So if the radius of the hole increases, the flow velocity also need to increase. And in our fourth experiment, we want to know how will the cross-section area of the water flow will affect the experiment. And here's the control variables, including the radius of the hole on the disk, the radius of the metal disk, the mass of the disk, and also the distance between the water pipe and the disk, and the initial depth of the water in the tank. And we're still going to measure the critical value that can let the disk to float in different cross-section area of the water flow. And after the experiment, we can see that if the radius of the flow increase, the requirements of flow velocity will decrease. It is because even the flow velocity is not that fast, but if the cross-section of the area of the water column is big enough, the flow rate on the disk will still be enough, and so that it will cause the enough pressure difference that can let the disk to float on water surface. And also, in the beginning of the fourth experiment, you might think that when you increase the flow velocity, you maybe will increase the impulsive force. But I think that in our experiment, the variation of the pressure difference is still bigger than the variation of the impulsive force and also the additional mass. And come discussion part. And we are doing an experiment. We have found some possible error that will affect the experiment. First one is a bubble in water. We observe that when the water velocity increases, there are many bubbles in the water, and we find that if there are many bubbles, you will form a lifting force. The bubbles will be like an air cushion, so give a disk a force like the lifting force, and it will cause a possible error, just like this graph shows. And the other possible error is because of continuity equation, so that the cross-section area of the flow is not fixed. And after our experiment data, we find that the distance between the disk and the water pipe is inversely proportional to the variation of the cross-section area of the water flow. Like if now the flow velocity is very small, maybe the cross-section area of water at here will be really small, so it will have a possible error. And also, even in the problem statement, it has said that the manual stick with the hole, but we want to know how will the hole affect the experiment. So we find that the main function of the hole on the disk is to stabilize the disk. Even without the hole, the disk can still flow on water surface, just like this video. And here's some conclusion. And we think that the pressure difference is the main force to let the disk to float. And the reason that will cause the pressure difference is because of the water velocity difference. So, and we can calculate the critical value of the water flow to let the disk to float. And after our experiment, we can know that the lighter the disk is, the easier the disk can float.
flow. And in the second term, we can know that if the radius of the disk increase, the requirement of the flow will need to increase to that disk to flow. And also, if the radius of the hole increase, the flow velocity also need to increase. And last one, if the radius of the hole increase, the requirement of the flow velocity will decrease.
Time's up.
Thank you.
2 minutes for question from the opponent.
Please can you please turn to your page 20. What is the red bar and the yellow bar in your chart thing?
Oh, you mean this red X and the green circle? And we are doing experiment. The red X means that in this water velocity, the disk cannot float. And above in the green circle part, it means that in that water velocity, the disk can float.
So the blue line is a theoretical line, or
yeah, and the fitting line, fitting theoretical line.
Fitting theoretical. Okay. And how do you make the surface of the water is steady?
I can say refer to question.
How do you make the assure the surface of the water is steady?
When we are releasing the disk, we won't really to affect the water a lot. That's just like these videos. We didn't really touch the water surface.
But the water jet you release will make the.
You mean the stability of the water surface?
Yeah.
Yeah, but you can see even there's not stability, but the disk can still flow constantly. And you will think it's just because there's no vertical water jet. So they will have no pressure difference.
But if you release your jet, how do you measure your velocity of the water jet?
Oh, velocity, please send to the setup page. Thank you. Setup page. Next page. So we use this to control the flow rate and use this to measure the flow rate and the flow velocity. So we can know the flow velocity.
Time's up. 3 minutes for preparation of the opponent. opponent, please take the floor.
Okay, I'm the opponent of my team. I'm going to talk about the unsinkable disk. This is a problem statement, and the reporter main focus on the force analysis and the limit of the velocity. The structure of solving the reporter solve their problem is that observation is that if there is a vertical water jet, it can make the disk flow. And their theory they use is Bernoulli's principle and the cross balance. The setup, their experimental setup is water pipe, water tank, and the metal disk. And the conclusion is that the lighter the disk is, the easier the disk will flow. The area, mass, and radius will affect the result. And the pros and cons of their presentation is the proposed is they talk about Weber number and they can ignore the surface tension. And we can see the trend from the chart. And they did several parameters and they talk about possible error. The cons they make that is they should explain more about the theory because it is quite complicated. And they didn't mention a lot how they get their velocity. And they should talk more about the chart. And there are few questions I want to discuss with the reporter. First is about the main factor of the phenomenon. In our experiment, we consider the vortex of the under the water in the water tank, and in our whole experiment, we consider many parameters that will affect this motion. And second question is what will happen if the width of the jet is smaller than the inner radius of the disk? And the fourth question is what is the major factor of the disk to fall? And while the water jet hits the edge of the hole, it will cause a friction. How do you think it will affect the result? And the last question is how to change the mass, but not to change the volume of radius or other parameter. And I want to skip into the discussion part. The first question is I want to ask the main factor of the phenomenon.
You mean how do I define the disk is flow or sink? Do you mean that?
I mean that what phenomenon will what's the behavior of the whole system?
Which parameter will affect the most?
Yes, and
just like all the parameters I do in my experiment, the radius of the disk, the mass of the disk, and also the radius of the hole in the disk, and also the cross section area.
What is the major of it? Major reason of it?
Okay.
Major reason that caused its flow.
I say the pressure difference. Just because of the velocity difference on the disk, and also the explanation. And here, because when the water hit the disk, it will spread out, right? So we have the flow velocity here. So but under the bottom, if the depth of the container is deep enough, even the water flow just go through it will just go down. You will not have a water convection or so at here at the bottom of the disk is almost no velocity. So from the Bernoulli principle, we can know that if the velocity is bigger, the pressure is smaller. So we can know that the pressure at the bottom is bigger than the pressure on top. So yeah, form a lifting force that led disk to float.
That is connected to our third question. And what will happen if the width of the water jet is smaller than the inner radius of the disk? It won't have the layer.
Oh, you mean just all go through?
Yeah, it won't have the layer.
At least the thing that depends. May I use a blackboard?
Sure.
Okay, thank you. If this is a container, it depends on two. If this is one surface and this is a disk. If the water all go through it, if the depth of the container is too small, and that may be when the water flow goes through, it will hit the bottom of the container or have a go back and have a water convection to let the disk to flow. And also, but if the depth is too but the depth of the container is too high, then the water will just go through it. But it's still possible that this situation that this can go, because if in our discussion part about the bubbles here. Okay, yeah, here. If this is the disk and this is the water, if the water all goes through the hole, but we said that if the water velocity is very high, it will cause many bubbles, and the bubbles will turn back and give a lifting force to the disk. So if we didn't reduce the bubbles, it's still possible that when all the water jets go through the hole, it's still possible that this can flow. But because we cannot calculate the bubbles, maybe the number of it, and how will it cause a lifting force, we didn't know how to calculate the force. So we try to avoid it. So we try to put some straws in the water pipe, and so that it will reduce the bubbles. So that we can reduce the possible error. But this part is still a little bit, but we think that that won't affect a lot.
So you mean the faster the water jet velocity is, it will cause many bubbles, and you might raise the disk.
Yes, and because we didn't know how to calculate the bubbles, so we try to avoid it. So we put some straw into the water pipe, and to make sure that the water is going straight in the water pipe. So when the water volume hits into the water, they won't have that much of bubbles.
In our experiment, the disk is easy to remove, or just crushed by the water jet. How do you
look at in our experiment? There's only two parts. If the disk is just going down or is just stable. In our experiment, the disk won't really shake.
Can you please show this video again?
Okay, yeah. And you mean why you come here? It's because we close down the vertical water jet, so the disk will sink.
Okay, let's go back to our question. While the water jet hits the edge of the inner hole, it will cause a friction that bring the disk down. How do you?
You mean the impulsive force? Just leave the disk and like that.
No. But this is a hole, and the water jet comes through it. May I use the blackboard? This is the inner hole. The water jet is come from it, and this little connect will cause a friction that makes the disk come down.
We think that isn't influence much.
Did you do so? You just ignore this effect, or you have to do some experiment to.
Because if you all go through it, the water flow won't touch the hole. You mean just feed it? If you draw like this, the water flow.
Even the jet is bigger. It also touches the inner hole. If your water jet width is bigger than the radius of the hole, it will also make some water.
You mean a friction here?
It might also cause some water go through it, and it will cause a friction.
Friction. You mean when the water flow goes down, it will
go through that hole.
Does that really influence this experiment?
Maybe we think maybe it will. Okay, it seems that we don't have the same technology.
And also about the bubble part, I want to say more about it. And we calculate the Reynolds number to see that the flow velocity is turbulence or the laminar flow, and we find out it's laminar flow. So actually our flow vertical water column is quite stable.
Question. How do you change the mass you change the mass? How do you change the mass but not change the volume of the radius?
We can if we have a disk and we have a hole in the center, right? And we can put many of the disks in the same and stick them together.
But it will affect the thickness.
The thickness in our experiment, this metal disk, the thickness is only 0.02 centimeters. So that means we even put two pieces of the metal disc, the buoyancy is still very small, so we can think of influence a lot. It's very thin, so the buoyancy we think we can almost ignore the buoyancy. And actually, in the theory we have calculated buoyancy, but in an extreme part, the influence is too small. The thickness is too small.
But when you put these discs together, the volume of it will change. The volume of it.
The volume of the disc.
The size of the. This is a disc, and here is another disc. The volume of it will change.
Yes, the volume will, just like I said, the buoyancy. Just the buoyancy. The volume will just only, I think you want to say that the volume will affect the buoyancy. The buoyancy, everybody knows that the volume of the disc is equal to the buoyancy. And the volume is too small. So they won't have any effect. And also the constant K. We measure the constant K, and we found that the constant is equal to the 0.00056. If you maybe think that the number is very small, but if we change the constant K is still influenced a lot. So we think that the K, the constant we measure is quite quite good, and it's quite fit to our experiment.
Can you please show in your page 22?
22. So my computer is old, so it's wrong very well. Okay. What do you want to say?
Why your line is go like this? If you use Excel to do this Excel line.
This is a fitting line, theory line. Zero. Just I already said that. See, we have this formula, right? And we know this formula, and so we only need to find the K, this K. So if we, and as I say, we measure the K is 0.0056, and so that if we just put the K in it, and we already know the other number of it, so we can calculate the flow velocity.
Can you use your this equation to explain your conclusion or the result of your experiment?
Which one? Conclusion. What you mean? From this, from the see. Okay. I'll explain this for example. See, the mg means the gravitational force, right? So if the mass increase, that means if we want to have the same velocity, and this means the critical value the critical value of the water flow that needs to let the disc flow, right? So if the gravitational force increase, the critical value to let the disc to flow, the water flow will also need to increase.
What is the deviation? What caused the deviation between your theory line and the experiment?
I already said in my discussion, the bubbles and also the variation of the cross-section area of the water flow. You see, I point here, and the next way I point here. Just because this one, the water is faster, you have more.
Okay, hands up.
Okay, thank you.
Opponent, please summarize the discussion in a minute.
We talk about the main factor of the phenomenon, and we talk our discussion. The answer is it's all, and of course it's about the mass radius, inner radius of the hole, or the velocity of the water jet. And if the radius of the jet is thinner than the radius of the disc, they say that the water will hit the tip of the container bottom. So the depth. So if the second question in the condition we mentioned in our second question, if we want to make it flow, if we need the lower depth lower depth container. And the deviation they talk about is that the more velocity will cause more bubbles. And the friction.
Time's up. 3 minutes for questions of the reviewer to go.
Thank you for the reporter and the opponent. First question I want to ask both for the reporter and the opponent. Will the depth of the container affect the results?
Yes, and so we in the experiment part we make sure that the depth of the container is deep enough so that it will not cause the water convection.
Is there any distance that you measure?
We have put some, some many pieces like golden, just like a powder, golden powder, and we use the water and we look from the side, and we clearly see that in this height, they won't have the water convection.
We think if in their condition, it need a very deep container. But in our condition, the smaller width of the water jet, it need the vortex, the water jet to hit the underground of the container to the vortex.
How can you make sure the unsinkable disk system is stable?
Stable. Place of the video. This is stable, and we will close down, stable.
Okay, so what about the opponent?
We think the stable situation is this won't move. The disk won't move and it flow very easily.
And then if the disk is small enough, will the disk still be stable or not?
You mean the disk small?
Yes.
What you mean the disk is smaller than the radius of the water column?
Yes.
Then of course the disk will just sink because there's no area to have the water, to not have the pressure difference. If this is the disk.
Thank you. And what about
same acknowledgement.
Okay. So I want to ask, what's the origin for the bubbles that came from the front?
You mean why will bubbles?
Yes.
It's just here about when and here's the disk, right? And here's water column, and maybe on the top here have many air, and when the water column will press down air, so we have many bubbles.
Thank you. What about
also a part that maybe.
Okay, thank you. I want to ask
the higher velocity of the water jet is you can transform to another kind of flow. The flow will be called vortex. It will not just like a stable water jet. It will become a different type, different shape of it.
Okay.
Okay, next 2 minutes preparation time for reviewer. Reviewer, please take a floor.
Thank you for the presentation. Today's problem is problem number 4, unsinkable disk. And so, okay, so for the problem statement, I think the problem statement tells us to investigate, explain the phenomena and investigate the relevant parameters. So for the summary and the comments for the report, and this observation and theory is observation video and the phenomena explanation, and the theory is force analysis and Weber number and fitting constant K and calculation of the mass and the delta and the pressure difference. And for the variables, first is the mass of the metal disc and the radius of the disc, the radius of the hole on the disc and cross section area of the water flow. And for the conclusions, you get this water velocity will cause pressure difference and variety the experiment results. So for the advantage and completely theoretical analysis and rigorous experimental process, and 3 is the multiple sets of the experiment data. And the 4th is well-prepared presentation, and 5 is full of theory. And for the suggestion, first is a clipboard experimental video, and the second is risky time for the risky time management. And for the summary and the comments of the opponent, first, opponent starts at his summary, and then is the strength and the suggestions, and that is the question for the discussion. And here's the advantage and the suggestions. First is right concepts for the theory, but for the suggestion, I want to suggest the opponent discuss more about the question of the theory, because I just see he wanted to discuss the connection between the theory and the experiment, and discuss more about the experiment data, and focus more on the reporter's work, and cannot catch the key points of the problem. And the 5 is keep asking trivial and technical questions. So for the summary and comments of the discussion, first of all is opponent asks what is the main factor of the phenomena. The reporter says pressure difference, and I agree with the reporter. I think that the main reason to cause this phenomena is the pressure difference between the water and the. So, and the second is what will it happen with the radius jet greater than the radius hole. Reporters answer that it depends on the extent of bubbles. I agree with the reporter because there is no flow on the top causing the phenomenon to rely on other manufacturers. And how do you think the friction will affect the result? And the reporter says the solution is not negligible. And for my opinion, this equation is not very important because the friction of the flow is actually against the jet. So for my question, will the deep container make the result change? In both of them answer yes, and I think it will not affect the result. So for the what is the origin for the bubble? I didn't get the response for the opponent, but because said air above this, so I don't think that this flow surface will influence, and creation is not obviously, so I don't think the bubble's force will affect the result.
The reporter please give the concluding remark.
Yes, the concluding remark. And in just like what I said, in the Weber number, we can undergo the surface tension of water when the Weber number is a lot big, when the Weber number is bigger than 1. And by flow meters on the pipe, we are able to measure the water velocity. Like these flow meters. And we have talked about the trend of the chart and explained it is the theory part. And the definition includes the bubbles caused by the higher speed of water jet and also the cross-section area of the water flow. And water doesn't cause friction, so we don't need to consider it. And when Typt rock is called field resistance, not friction, sorry. And the volume of the disc eddy is small, so that the buoyancy of the disc won't affect the experiment run. And I want to repeat a part that I say wrong. I said the bubbles, I say it's because the air above the disk, but yeah, I think it's possible that they have the air that's in the water, because we provide the water from the water tap, and maybe the water pipe didn't connect with the water tap very tight, so maybe there's bubble, maybe it's caused by the air in the water flow. And here's my and this is my presentation. Okay, thank you.
Okay, so next, it's time for questions of the jury.
Do you see the show page 13?
Page 13.
What is the variable C?
Oh, you mean the data? May I use the blackboard?
Yeah.
Because we think that the angle that's the surface tension, the theta is the 13. The theta is the angle that the surface tension pull the disk. Because it would be like this if you put the disk right here, and we say that here is the theta. And so when we are doing the theory, we have right. So we calculate with that is the cosine of theta. It's cosine theta. I'm sorry.
So what's the theta in your?
Just the angle. The angle that's the surface tension for the disk. The surface tension.
Okay.
Yes. I didn't explain well. Sorry.
Page 22. Page 22. What's the 22? What's the radius?
22.
What's the radius of the hole?
The radius of the hole is just the radius of the hole is the
Yeah. Page 22. Yeah.
You mean what's the radius of the hole? It's the radius
for the data on page 22.
You mean the radius of the hole? What is it? Just the radius of the hole on the disk.
The radius of the flow, water flow.
And that means
Could you show page 22?
Okay, sorry. You mean the radius of
So the x variable is the radius of the hole.
yes.
So what is the radius of the water flow?
I know what you mean. So if
In this data, just
you mean radius of the hole or radius of the hole?
the radius of the water flow in this data.
Cross section area. The cross, because if this is the water flow, it may the circle and the radius of the water flow.
Yeah.
So what is the radius? What is the value of radius of water?
Water flow.
Here the A.
No. This
Value. Okay.
那个水流的半径有没有里面有没有量啊？
你这边的变数是那个动的半径啊，不是水流的半径。
So the radius of the flow we do in the experiment 4. You mean here? Yes, we control variable is the radius of the water flow. Means the cross section area means the if this is the water column, just the water column is the same.
0.85 centimeter.
Yeah, just 0.
Yeah. Next week.
And
So it's much larger than the radius of the hole.
you mean
A meter.
oh, here is the meters. Sorry, I didn't explain well.
Any further questions? Boundary.
Thank you. So how do you measure this radius of the radius of water flow?
Oh, what? Turn to the experiment, equipment part. We measure the radius of the water pipe, the inner radius of the water pipe. Inner radius.
So would that be the same as the radius on the disk?
Just like on the discussion page. Oh, I also need to say that yes, this also have a little difference. So when we are doing the experiment discussion, we put the water pipe very close to the water surface so that the cross-section area of the water flow won't change much. Just next page, just like this says. So because they have a variation of the cross-section area of the water flow because of the continuity equation. So when we're doing experiment, and this is to see that this graph just to let you to see that the variation. So when we're doing an experiment, if this is a water pipe and we try to make the water surface very close to the water pipe, so that's the variation won't be very much.
Okay, so if no more question, now it's scoring time. Okay, for reporter. 8, 7, 8, 8, 7. For opponent. Opponent 5, 6, 6, 6, 6. For the reviewer. 7, 6, 7, 7, 6. Okay, now take a 10-minute break.
是啊。交给你的许多，我相信你。你看你拿这个哪知道？你的省钱就看这一招。但你那个你有没有去新公园？我有出来打，对，我是没有打完再学比较。是这样吗？可以。是啊，我没事做。我们班明天听完别人就回答。看一下。是哦。 先轻松一些。
他也确定可不可以，要不我重新看电脑。
出水管的时候，然后就整个它堵太快了。水管的然后跟你看上那个是完之后不一样，然后该准备最上面的话，里面比较觉得它对它有比较大。
你帮忙给我。是啊，礼拜五的。哇，那也。没天没天。哦，两个对。我刚才发现也对。应该有看到不少不错的。
那今天打那个
这个公主是有几个人来？啊，我他们就是人这样。
你说刚那个什么？
应该很多人吧？
你的月卡，对啊，然后你。上票的，对吧？主教也可以。
然后加起来。
不用洗，如果人家问我，在回答的时候再说出来。可是如果的那些parameter的东西一一写在上面，那你不讲，那是有点奇怪。对不对？他说你待会再讲，回答。那你写在上面，然后你也没讲。还有他写对。那要不就是说你把上面说好，你就是很重要的哪一些 key parameter。那还有就是你讲那个图的时候，你看对方那个人还要问你说那个红的、蓝的是绿的是什么？是你有标出来，可是就是说他都没有办法 catch， 他是你的 opponent， 他都没办法 catch 你那个是什么？那等于说这个是要有改善空间的，就是说你讲字的时候可能太快了。你觉得你有讲，但是他没办法知道，而且你的那个 line 呀，他怎么算的？毕竟是你看，你都说是你的 theory 是 prediction line，那你 你要 fix line， 那 fix 是它的一个两个 data 中间，然后这中间你把它 fix 出来了，还是你那个是 theory？
在秒指它那个
长度可以determine 嘛？对啊，那就是你的 theory line 啊。所谓 fix line 是说，你这些 data 都用出来之后，我从我这个 data fix 出来的。
我们可以从一个时间 fix 到 fix 所有的。就是还有。
你要讲清楚啊，这有两个东西，一个是说我把 fix 出来之后，然后我带进 theory， 然后把这个线画出来。另外一个是说，我有这些 data point， 我也不晓得比例的怎么样，我就一条 line， 把它比例也 fix 出来。那你这两个就没有讲清楚啊，对不对？你说 fix 出来，那 fix 出来那有两种意思。那我会比较倾向后面那个意思，就我有一个 data point， 然后我不晓得比例怎么样，然后我 fix 出来线，那你会让人家觉得是这样的。对，后来是因为这样子也不晓得怎么做，不过高老师都还在想自己的，因为他想说看在这个如果他开放的话更好一点。对啊，反正我是说，觉得他在更降级的时候，对啊，就说除了这关系之外
Okay, now is the final stage, in this afternoon. And firstly, the reporter please prepare your presentation in 5 minutes. And please write down your name on the blackboard. 你先选人，选不到他对不对？他没有没选，他是在上面，他现在不能选。那你先选另外一个，另外一个人先选，那你进。打给那个俊明，赵建明，俊明，就是他现在有一个技能，就是没有办法选一辆车的那种，就是那个功能那个我觉得很好就是就是动子，动之间的。虽然它是反白的人，
I would like to start the presentation.
Okay, so reporter, please give the presentation in 12 minutes. You can start.
Good evening, everyone. I'm from Typt. Today, I'm going to present the handle power theory. And this is our problem statement. A paper spiral suspended above the handle starts to rotate. Optimize the setup of maximum torque. And our main focus is in what conditions can lead to the maximum torque. And this is our outline. And first, we're going to talk about our observation. The paper spiral will depend on a spirit lamp, and the heat from the spirit lamp will make the paper spiral rotate. Okay, then this is our theory. First, I'm going to talk about the inertia of a paper spiral, which is given as the following equation. And about the kappa, we're gonna make it a constant because the paper spiral is made of the same materials. Then next, we're gonna talk about the angle of acceleration of the spiral. The angle of acceleration of the spiral is omega over time. And then the torque of the spiral can be calculated as the inertia, angle of acceleration. And this is our experimental setup. In this picture, you can see we have three spirals, which the radius is 4, 6, and 10. And this is all made of crystal board. And under the spiral, there will be a spirit lamp, which will provide the heat to make the crystal board rotate. And on top of that, there will be a friction line hanging the paper spiral. Because the friction line will not provide that much friction, so I think that will be a good material to use. And that's all variables. Our independent variables is the length between the spirit lamp and the paper spiral. Next is the different radius of the paper spirals. And then our dependent variables is omega. And this is our data analysis. First, we're gonna talk about the length between the spirit length and the paper spiral. And I'm gonna talk about why we use 10 turns and another 10 turns in the graph. Because in the first 10 turns, there will be no velocity in the beginning. And after 10 turns, the velocity will increase because we have the velocity from the beginning and plus the heat that have given the spiral another velocity. So we have plus the two data to find the average of that. And you can see with the radius of 6, they will have the fastest rotate velocity. Next is the length between the spirit length and the paper spirals. As the previous graph, the spiral with 6, the spiral with the radius of 6 will turn the fastest. And then the length between the spirit length and the paper spiral, 20 centimeters. And then, just like the previous graph, the spiral with the radius of 6 will also turn the fastest. And then we compare with the graph before. Which one? You can see with the distance of the spirit length and the paper spiral increases, the turning speed will be slower. Okay, next, I'm going to talk about different angle accelerations in 4 different depths. As the previous 3, we will find the average of the 10 turns and another 10 turns, because the velocity will affect it. And as you can see, with the length of 20 centimeters of paper spiral, the angle acceleration will be the fastest. And then the angle acceleration paper spiral radius is 6 in different depth. And then we can also see the length with 20 centimeters will also be the fastest. And the last one, we can still see the same result as the previous 2. Okay, and now is our discussion. According to our data analysis, we found out that when the length between the spirit length and the paper spiral is 20 centimeters, we can get the largest angle acceleration in comparison to the other 2 lengths. Also, we can find out that the angle acceleration has the same sort of length, with like 20 centimeters is bigger than 10 centimeters and 30 centimeters. So we would like to investigate deeper into this phenomenon in the future. And that's our conclusion. No matter which radius of the spiral, the length between the spirit length and the paper spiral is 20 centimeters. It gets the largest in comparison of the 2. And then, when the paper spiral has a radius close to 6 centimeters, it has a length of 20 centimeters. It gets the maximum torque in our experiment. And the torque will have a sort in which the length of 20 centimeters are bigger than 10 centimeters and 30 centimeters. And this is the end of my presentation.
Okay, next 2 minutes for question from the opponent.
Thank you for recorder. We'll turn page 4. Yeah. So, could you tell me that what is the difference between these 2 spirals?
Okay. And the spiral in the right has the bigger radius, and in the
So
left.
which one has the biggest radius?
Sorry. Okay. It's not radius, it's the length of the paper spiral and the spirit.
How do you change the length?
Oh, we will hold our fishing line higher.
Okay, so they are the same radius board, and then you have a different length.
Oh yes, they have the same radius and we control the length.
Okay, we'll turn to the next page. And could you tell me that what the theta max means here?
Oh, the theta max. Okay, because in our graph we use 10 terms and we consider theta max as that it has rotated for 10.
Could you point out that is that the page, or you can point out where the theta max is? Or is where the theta max you can, oh, where we can move to the next. So could you turn to the next page? How do you cut the board?
Well, we cut the board by scissors and we just try to control the length of it.
Okay, so and then the next page. And so how do you depend? Why is the omega dependent?
Time up. 3 minutes for preparation of the opponent. Opponent, please take the floor.
Okay, so good afternoon, everyone. I'm the opponent from Team Lighting. And today I'm going to introduce the problem 13 candle power turbine. And we can first look at the problem statement, which the reporter had mentioned before. And I think that the problem statement also mentioned about the maximum torque. And here's the summary and the comments of the report. And the first is the theory. The nature of a paper spiral, the alpha of the spiral, and the torque of the spiral. And the variables that then change at the experiment is the radius of the spiral and the length between the spiral length and spiral. And third is experiment. And here are some data analysis. And that's the conclusion. The length between the spiral length and spiral, if it is 20 cm, it gets the largest torque comparison with the other two. And advantages for the report is provides a sufficient amount of experimental data and a complete conclusion. And my suggestion to the report is an experiment process not rigorous and insufficient theory. And that's a correlation between data and theory not shown. And some missed point I want to raise. The first about the theory, I want to raise about will the heat of the candle change the rate of the turbine? And next is the data. The first is how do you separate your experiment from the surrounding airflow? Well, from the picture, I didn't really see that it looks like in an open area. I think that might be something to disturb the experiment result. Next is, will the distance between the paper and the candle change the rate of the turbine? And that's why do you use the spiral length in your experiment? Because the problem statement has mentioned about using the candle. And so I wonder that why they choose the spiral length rather than the candle. And the experiment and the parameters part. The first question I want to raise, which parameter depends the direction of the turbine spinning? And can we change the candle to other tools that also makes the end flow? And that's all my report. Thank you. So thank you for your order. I want to ask why do you use the spiral lamp and not the candle?
Because candle will melt, and if the candle melts, the height of the distance of the paper spiral and the source of heat will change.
So if we didn't, except for the height that the candle will change, the other physical characteristics, they are really similar. Is that right?
Candle and paper spiral might be similar.
Okay. And the next question. So you think that using the spiral length won't affect the result?
Yes.
And you have ever considered to using a different material to the board?
Oh, yes, we did use different materials, but with softer materials, it will easily fall down. And with harder materials, the experiment will not turn so easy.
And if we change the mass of the turbine, do you think that will affect the torque?
Excuse me.
If we change the mass of the turbine, do you think that will affect the torque or other results?
Yes, I think it will.
Like what?
The result, like the angle velocity will affect.
Will decrease or increase?
With the increase of mass, the velocity will decrease.
Okay. And next is, because your experiment has only used 3 different types of the radius, and for these 3, you have mentioned that at the 20 centimeters as the best to spin. And if we think about using 40, 50 or more, or using 5 centimeters, do you think that will have another better turbine?
I don't think that using smaller paper spiral will be better, because with the smaller paper sphere, if the area of the heat hits the paper spiral will not be that much. And with the longer of the distance, I think the heat will evaporate in the air.
Okay. And please tell me how you so do you hang the turbine?
Oh no, we.
Or could you just draw on the blackboard?
Okay.
Your experiment setup.
No problem. Okay.
Okay, so you hang the spiral.
Yes.
And then how do you connect the, is that thread or?
Oh, that's just anything that can not let the rod fall.
Rod fall?
No. We use the rod to change the friction line and
Fisher, so that's a Fisher line.
friction. Yes.
So how do you connect the Fisher line with the turbine?
On turbine we have it is a circle inside from here, and here there will be a little hole, and we use the friction line. We put over the friction line and yes.
Okay, and we all know that the turbine will spin and will have a torque. And but when you hang the turbine, the Fisher line will also have a torque. So it might be tend to rotate back. Do you have consider about this situation?
To that it will from very beginning it will not really impact because the friction line can actually turn maybe. Yes.
So you think that the torque will might affect the result?
No, the torque will not affect the result because that is small enough to let us don't consider it.
Oh, so you mean that the Fisher line torque is too small to consider?
Yes.
And could you tell me that how small that you can just ignore it?
Like because we didn't have the actual data, but the friction line can.
Okay. You guys say that you changing the different length of the turbine.
Yes.
And we can know that when the turbine maybe is like this, and there will be a slope, and if we increase the length, the slope might be bigger. Slope is so do you think that the slope will influence the result?
Yes.
And do you have how will that affect?
How will it affect?
Like if we increase the length so that be more easy to rotate or harder to rotate?
Let me draw that.
Okay.
Did you just say the length of the spiral and the heat?
I think is maybe you can just say that if you increase the length of the turbine, will that be easier to rotate or harder to rotate?
If you increase it, I think it will be harder to rotate because the heat will just evaporate in the air.
Pardon?
The heat, with the distance it goes, the heat will.
And I think that if we, so why do you think that the turbine will rotate?
Because there's confession that makes the spiral rotate.
Could you say that again?
There's the heat compression to make it rotate.
And could you draw the heat compression?
Sure. And this will be the force to push it.
Okay, so do you think that because we know that if the turbine ends here or in the other, do you think that will affect the direction that the turbine rotates?
Yes.
So if it ends at the right side, and will it turn clockwise or the other?
And let's consider the turbine just like this. Okay. And if the heat is put in here, it will go clockwise.
Alright. And I have some suggestion for your experiment. The first is that because we can see that you cut your board with a scissors, but sometimes it's pretty hard to control the width of every part of the turbine. And I think that maybe we can use a laser cut to cut the board more even.
Because the laser cutter will burn the paper, so we don't consider it.
Okay. And I think that because you have mentioned about the torque of the pressure line, you say that it's really small to ignore this. But you still have the value that to prove what you said. And right? Yes. And I think that if we have a stick and use a magnetic thing to, and there's a nail, and we can set it, and that won't really cause a friction. And so because if we only use like a stick and just put it on there, and that might cause some because we need to have a if we have a like put on the stick, the turbine might have a little hole on the top, and thus that might make some friction. Yeah, the friction and also the moving of at the top of it. So if we use the magnet thing to stick on that, and it will also increase the friction and affect the results.
I would like to ask, when your experiment instead of when your spiral touch the rod,
you mean which one?
this one.
Oh, yeah, you will touch the rod.
And how can you avoid the friction about it?
Oh, because yeah, that's at the flaw of the experiment setup. So I just suggest to use the magnet to connect the spiral and the.
But then, like I said, there might be some contactile point over here when it rotates.
Like that. So next, opponent, please summarize the discussion in a minute.
So from discussion with the reporter, we discussed about more about his experiment and like the length of how the length of the spiral affect the result. And so I asked him if he do more radius of the disc of the board, would that affect the result? But he said that too small is not good and too big is also not good. So I think that he said that at the 20 centimeters is the best. And then also because I also point out some talk about the pressure line, but he said to ignore this. But I gave him some suggestion to use other kind of the experiment setup, and I think that kind of good. Thank you.
Okay. So 3 minutes for questions from the reviewers. Propose.
Okay, for a question for a reporter, do you think air drag can affect the experience?
I think
Yes or no?
it will, but not that much.
Okay, so your page 5, you measure the torque by I alpha, right?
Yes.
Oh, then I use the blackboard. When you are using the torque equals I alpha, and you calculate the angular acceleration of the spiral, right?
Yes.
But don't you think, like you said, the air drag will affect, and don't you think that the air drag will affect the angular acceleration and then affect the torque result?
Because air drag, yes, it will affect, but the air drag will not
very
affect. Yes.
So, and also I want to get another measuring method that is tau equals kappa theta, which is the string torsion. Like when you are in your experiment, you use a line to hang the spiral, right? Then why don't you just use the string torsion to calculate the torque? Like if this is the torque that the fishing line gives to the spiral, then it would equal, when the spiral spins, it would be blocked by the torque that the string gives to the spiral. And then it would cause a balanced angle that would be equal to the torque that the handle gives to the spiral.
We didn't think of that when we were doing the experiment. I can go into that.
So can you, for a reporter, can you quantify the force given to the spiral? Okay, never mind. Dude, can you quantify the force given to the spiral?
Yes.
Yes, and okay. Okay, never mind. Next question. For the reporter, would you agree that the paper spiral's angle of inclination in each point would be different, like the angle that the spiral strip?
Yes.
And then, did you try to control the tilting angle, like the tilting angle of the spiral?
That's too hard to control, so we didn't consider that.
But since the tilting angle will affect the magnitude of the force that acting on the spiral. So the reviewer thinks you should control it. Then, for the question for the opponent, do you think the opponent and reporter, do you think the location of candle can affect the
Time's
result?
up.
Yes.
Okay, 2 minutes for preparation of the reviewer. Reviewer, please take the floor.
Honorable juries and fellow competitors, I'm the reviewer from Team Excel here, and today I'm going to review problem number 13, candle-powered turbine. And the problem statement, a paper spout suspended above a candle starts to rotate. Optimize the setup for maximum torque. And we are mainly focusing on what are the main factors that affect the rotation of paper spiral, and in what condition will the paper spiral reach the maximum torque. And this is for the recorder. And for the phenomenon, he talks about the rotational motion. In the theory part, he talks about the moment of inertia, torque of the spiral, angular acceleration. And for the experiment, he do the radius of the spiral and the length between the candle. And these are the pros and cons for the recorder. He has a clear observation video. However, he has no quantitative theory, and he has lack of analysis about the candle's property, and also he had lack of method of changing the radius of the spiral, and that affects the math. And also, he did well on explain each relevant factors. However, he didn't measure the air drag and the friction, and then he didn't explain the deviation in the experiments. And for the opponents, he points out the recorder's experimental error, and he directly breaks down the problem statement, which is the maximum torque should be conducted by candle. And for the cons, he missed the discussion of the procedure of measuring torque, and he has inefficient time control, and also he lack of personal input in the discussions. And for the first discussion about the method to conduct the experiment, the opponent asked how wouldn't the string, the torque of the string influence the result. And the reporter said it won't affect that much. But the reviewer disagrees with the reporter since the fishing line will give a torque to the spiral, and that affects the rotation. And also, next page. And the discussion about the mass of the spiral, the opponent asks, will the mass of the spiral affect? And the reporter says yes. And the reviewer agrees with the reporter since the mass will affect the angular acceleration when in the rotating motion, and the moment of inertia, which he used to calculate the torque. And for the discussion about air drag, the opponent asks, do you think the air drag would affect the result? And the reporter thinks that he don't think it would affect that much. And then the reviewer disagrees with the reporter because when the air drag will affect the rotating motion of the spiral, and that affects the angular acceleration that he used, the measuring method he used in the experiment. And so we think it would affect. And for the point missed, in the discussion they missed to discuss about the convection, which we think is the most important factor in this experiment. And he didn't talk about the temperature, how the temperature of the environment affects. And for the setup of maximum torque, they didn't discuss about using other measuring methods such as using string to calculate the balance angle. And for the deviation, they didn't talk about the deformation and the friction, and also the air drag that affects the rotating motion of the paper spiral. Thank you.
Okay. So next, the reporter please give the concluding remark in 2 minutes.
Okay, so this is our concluding remarks. First, omega max is considered to the maximum. Theta max is considered to the maximum spin angle of the paper spiral, which is 3,600 degrees, which is 10 laps. And the second, candle will melt, but we want to control the distance between the spiral and the heat. And third, if the paper spiral is too small or the distance is too long, the heat wouldn't be distributed evenly. Fourth, the slope of the turbine will affect the angular velocity. The next one, about the experiment setup, we surely have places to improve on in the future. And thanks for your suggestions. And the next one, details about our theory can also be improved. We will fulfill the experiment in the future. Okay, and this is our concluding remarks.
Okay. So next is time for questions from the jury. Okay, so maybe I ask one question to opponent. Do you think what is the driving force to let the paper rotate in this experiment?
When the air is because we use the heat to heat the air, so when it goes up, it will hit a spiral and give a force here. Plus, we can know that as a Newton's third law, it will give another force here. So I think that why the spiral will rotate.
Yeah, so I mean, what is the driving force, the physical factor?
Give me a second. I think it's the air force caused by the convection.
Okay, so how about the viewer?
I think the main force that causes the rotation is the horizontal component force of the air impulsive force, which goes upward, and the horizontal force is this way, and it causes the rotation of spiral.
My opinion is, the major reason that makes the spiral turns is heat convection, which hits the spiral.
Okay. Any further question from other jury?
Okay, so in your experiment, you data show the length between the length and the ball.
The spiral
is 20 centimeters in paper, right?
Yes.
Okay. So do you think 20 paper is the optimal?
I think it will. Our experiment shows that 20 centimeters is surely the maximum of, can make the maximum of the angle velocity.
Would 18 or 22 better?
We didn't think that.
Okay. So how about you guys? So what do you think? Because basically you guys can do experiment, okay, and then
Okay, any other questions?
What is K in your
It's kappa.
what is kappa? Page 5.
It's torsion coefficient. Torsion coefficient.
No. The page 5, there is a K for kappa.
Well, we consider that as a constant because we use the same material to do the experiment.
Could you show page 5? Yeah, K. K.
Well, we consider that as a constant.
So you didn't measure the value. You do not have the exact value of K or kappa.
No.
Yeah, because I cannot see the variable of the size or the length or the mass of the spiral in this formula. Because the moment of inertia should depend on the size, the width of the spiral or the mass of the spiral.
Any further questions? If not, okay, it's scoring time. Okay, for reporter. 5, 5, 6, 6, 4. For opponent. 8, 7, 7, 6, 7. For reviewer. 8, 6, 7, 7, 8. Okay, so are there any comments or opinion from the jury? Yeah, to give the students. Okay, so if not, now let's thank everybody to participate at this event. So thank you very much. It's end here.